Resistors are simple components, right? If you think so, you have to watch this video to the end because you are completely wrong. Resistors are used for limiting current. This is the most basic definition of resistors that we have already heard of, but this is so ambiguous. What does it mean? What else a resistor can do in a circuit? Where in a circuit you have to put a resistor. In this video, we will dive into the world of resistors, skipping the technical jargon and explore their application. We will cover 6 main types of resistors and explore 16 examples of resistor usages in circuits. Stick around to uncover the true versatility of resistors in electronics. Let's get started. Materials are divided into 3 categories: insulators, conductors, and semiconductors. Semiconductors are used for building components like diodes or transistors. They are not subject of this video. Insulators are materials that have ideally infinite resistance, and conductors are materials that ideally have zero resistance. Actually, there is no ideal insulator or conductor in the world, and normally every object or material has a finite and non-zero resistance. Don't blame me for superconductors or super insulators. They are laboratory exceptions. So let me call any material in the world a resistor. From high resistance materials like rubber, plastic, or glass, which are called insulators, to metals, which are normally called conductors. So in this video, we will consider anything as a resistor. These are what we usually refer to as a resistor. Each resistor has a value in ohms. This is ohm symbol, and this is a schematic symbol of a resistor. In real life, the resistance value of these resistors can range from significantly low to notably high. The value of each resistor is determined by these colored bands. The first application of a resistor is to limit current flowing to sensitive components. Let me give you the first example, which is so predictable. Example number 1, limiting LED current. This is the simplest example of resistor usage ever. We can't connect an LED directly to voltage sources like 5 volts because the forward voltage of an LED is much lower than 5 volts. By connecting 5 volts to the LED will try to draw infinite current, and this will destroy the LED. We have to put a resistor in series with the LED to protect the LED from overcurrent and burning. It's not just ordinary LEDs. All types of LED displays obey this rule, including 7-segment displays and other types of LED monitors. Also, it's not just LEDs. Resistors are used to limit current to other components, and sometimes they are used to limit the charge current of a battery for safety purposes. Anyway, let's move on to the next example. Example number 2, base resistor of a BJT. Typically, a resistor is placed at the base terminal of a bipolar junction transistor for various reasons. Sometimes it is used to limit the current flowing to the base terminal, protecting the transistor from damage. Other times it is employed to configure the transistor to operate within a specific region. This is a diode model of a BJT. Actually, there is no diode here at the base emitter junction, and also there is no diode at the base collector junction. But base emitter junction and base collector junction are acting like a diode, something like an LED. For the same reason as the LED, we have to put a resistor here at the base terminal to protect the BJT from burning. Sometimes we need to keep the voltage at a specific point of the circuit equal to a desired value. For example, sometimes we need to keep the base voltage of a transistor equal to 0.7 volts to make the transistor operate within active region of operation. Also, in this case, resistors are ready to help us. Now is the time for the next example. Example number 3, using resistors to bias a transistor. One of the coolest applications of a resistor is to use it to bias a transistor. What is biasing? What it is good for, you may ask? Let me explain. There is a misunderstanding about BJT transistors. Most of newbies think that there is a threshold voltage at the base terminal of a transistor, say 0.7 volts. Applying voltages greater than 0.7 volt will turn the transistor on, and applying voltages lower than 0.7 volts will turn the transistor off. But this is not true. Actually, there are two threshold voltages here. By applying voltages lower than 0.6 volts, the transistor turns completely off, and by applying voltages higher than 0.8 volts, the transistor will turn completely on. But there is a voltage range here from 0.6 volts to 0.8 volts, which the transistor is partially on. This region of operation of a transistor is called the active region. To keep the transistor in active region of operation, we have to keep the base voltage in the middle of these two thresholds. After that, by applying a tiny signal here to the base terminal, the voltage at the collector terminal will be amplified and an inverted version of this tiny voltage. To keep the voltage at a specific value at anywhere of a circuit, we can use resistors. By connecting two resistors in series and applying VCC and ground to the endpoints, a voltage will be created at the junction point of resistors, which is calculable using voltage divider network formula. To have 0.7 volts at this point, the R1 resistor has to be 1 kilo ohms and the R2 resistor has to be 6.142 kilo ohms. This setup will keep the voltage at the base terminal equal to 0.7 volts, and then the transistor will be ready to amplify any signal. This structure is called a voltage divider network. We will refer to this structure many times in this video. In cases like this, where we need two resistors in series and we have to set resistor values very precisely, like this R2 equal to 6.142 kilo ohms, we can use a potentiometer instead. A potentiometer is actually a resistor with a wiper like this. By turning the handle, the wiper slides on the resistive surface and it changes the resistance between the middle terminal and the side terminals. Suppose that VCC and ground are applied to side terminals. By turning the handle clockwise, R1 will grow and R2 will shrink, causing the voltage at middle terminal to increase. And by turning the handle counterclockwise, R2 will grow and R1 will shrink, causing the voltage at middle terminal to decrease. As you can see, by applying this tiny blue signal with a peak-to-peak amplitude of 0.2 volts at the base terminal of this transistor, the transistor generates this large yellow signal with amplitude of 4 volts. These two resistors, R1 and R2, are called biasing resistors. There are endless points about transistor biasing circuits. I have described many of them in a separate video where we built a megaphone using transistors. There is a link to that video in the description. Anyway, the next example is about audio systems. Think about digital audio systems. Sounds and music are stored in a digital memory in a form of digital ones and zeros, and when we press the play button, the audible sound coming from the speaker is analog. So there should be something to convert the digital data to analog voltages. Resistors can do this task easily. Example number 4, using resistors to build a DAC. One of the fantastic application of resistor is to use it to convert digital data to analog voltages. You may wonder how it is possible. I'll explain. Let's see the example. This structure is called a resistor ladder digital to analog converter. By applying digital data here at these inputs, the corresponding analog value will arise here at the analog output. The number of digital inputs is changeable according to the project requirements. Here, I'm going to make an 8-bit digital to analog converter using 1 kilo ohm resistors and connect an MCU to make some waveforms. As you can see, this waveform produced by the microcontroller is actually a series of digital bytes which are put at the GPIO pins. It's the ladder structure that converts the digital data series to the analog voltages. You may wonder why I have used 1 kilo ohm resistors here. Actually, there is not a big difference between different values. Very low values will cause more power dissipation here, but it will offer stronger voltage signal at the output and be able to deliver much more current. On the other hand, higher resistance values will dissipate lower power, but the signal at the output will be weak. Lower resistance values will result in lower output impedance, and higher values will result in higher output impedance. The output impedance is not a big problem because it can be reduced by using an op-amp. It's very easy. Anyway, this was a way to make analog voltages like music signal using resistors. Now think about making two analog voltages using two separate resistor ladders. For example, two separate music. If you want to mix them to play both of them simultaneously, what we can do? Are resistors still helpful? The answer is yes. Example number 5, using resistors to mix analog signals. This is the simplest signal mixer circuit ever. It consists of two resistors, this one and this one. These resistors are here for attenuating signals so they can mix easily. I'm going to apply signal from previous experiment to point A and another signal generating using my function generator to point B to see what will happen at point C. As you can see, this is the signal at point C. If the resistance of these two resistors is equal, then the signals will mix equally. But if the resistors are not equal, a signal with a lower resistance in path will affect the output more than the other. You can use potentiometers instead of the fixed resistors to have more control over the output signal. As you can see, by turning these potentiometers, the output signal changes. We can mix an unlimited number of analog signals using resistors and build a simple version of these audio mixers. No, just kidding. These audio mixers are very complicated. Anyway, suppose that you build an audio mixer like this and realize that some noise exists at the output signal. What can you do? Are resistors still useful to remove noise from the signal? Example number 6, using resistors in RLC filters. RLC filters are some kinds of simple signal manipulation filters that consist of only resistors, capacitors, and inductors. They are used in many electronic designs for several purposes. One of the main elements of an RLC filter is the resistor, which is mainly used to attenuate the signal to make it easy for capacitor and inductor to manipulate the signal. There is a full video describing RLC filters in the description. Anyway, let's move on to the next example. Example number 7, using resistors to configure an op-amp. Operational amplifiers are excellent tool for every electronic designer. They can operate in two modes, voltage comparison mode and voltage amplification mode. For now, I'm going to consider amplification mode because some resistors are required in amplification mode to configure the op-amp. Look at this example. The op-amp is configured to amplify tiny positive voltages at this input terminal. The gain of the amplification is set by using these resistors. By setting the desired values for these resistors, the gain will set to the desired value. By setting RB equal to 1 kilo ohms and RF equal to 4.7 kilo ohms, the gain will be equal to 5.7. There is a full video about op-amps where I have described the application and modes of operation of op-amps. There is a link to that video in the description. Anyway, I'd also like to cover power resistors today. You may have seen these fellas, right? They are used in many applications where the resistor has to dissipate a huge amount of energy. Sometimes we need to simulate a load using a power resistor, for example, in simulators. Example number 8, using power resistors as a load simulator. Imagine a repairman who is about to fix a refrigerator's mainboard in his workshop. Most of home appliances nowadays are smart and their mainboard has several feedbacks from several parts of the device. For example, the ventilation fan of the refrigerator has a certain impedance, and if the fan is not in the circuit, the board is likely to stop working. So the repairman can use a proper power resistor to trick the mainboard into thinking that the fan is in the circuit. This is awesome. Anyway, resistors can be more exciting if you use them as a sensor. Example number 9, using resistors as a temperature sensor. Almost every resistor is sensitive to temperature. I mean, by changing the temperature, their resistance changes. But there are special resistors that their resistance depends on their temperature extremely. NTCs and PTCs are a good example of such a sensor, which are called thermistors. This is an NTC, actually a temperature sensor, which is called a thermistor. This instance has a nominal resistance of 10 kilo ohms. It means that at a specific reference temperature, usually 25 degrees Celsius, it has a resistance about 10,000 ohms. As you can see, the resistance of this component is more than 10 kilo ohms. It's because of the temperature at this place, which is a bit lower than 25 degrees Celsius. Look, when I hit it up, the resistance of this component decreases, and when I cool it down, its resistance increases. Thermistors are not the only sensors that are made based on resistors. There are plenty of other resistive sensors available on the market. Example number 10, light-dependent resistors. Another resistive sensor that is widely used is the LDR, or light-dependent resistor. The system of operation of an LDR is very similar to that of an NTC. It's a variable resistor, right? And its resistance depends on the illumination level of the environment. But there is a problem here. We can't use a variable resistor as input to an electronical circuit, so we have to convert the variable resistor to a variable voltage and then use the variable voltage as input to the system. This is an LDR. I'm gonna test it using my LCR meter. As you can see, by increasing the illumination level in the environment, its resistance decreases, and by decreasing the illumination level, its resistance increases.
By putting another resistor in series with the LDR, you can make a light dependent voltage. Then you can use this variable voltage as input to the system. For example, by using an op-amp in comparator mode, you can make an automatic light, or by reading it using ADC, you can make almost anything. This potentiometer produces a reference voltage from 0 volts to VCC depending on the handle position, and this circuit produces a variable voltage according to the illumination level. On the other hand, this op-amp will compare these two input voltages, and if the voltage at the non-inverting input is higher than the voltage at inverting input, it will activate the output. As you can see, the circuit works fine. When I cover the sensor, the motor starts to run, and when I uncover the sensor, the motor stops. But there's a small difficulty here when the reference voltage at non-inverting input is very close to the sensor voltage at inverting input. Look, the relay at the output turn on and off like crazy. Can you hear that?
Sometimes, because of some noise in the environment or some physical movements caused by the wind or something, the sensor voltage fluctuates a bit. When the sensor voltage is far enough from the reference voltage, there will be no problem because the entire voltage and its added noise will be separate from the reference voltage. No matter it's higher than that or it's lower than that. But when the sensor voltage is close to the reference voltage, it's likely that in some parts of the noise period, the sensor voltage gets higher than the reference voltage, and it will cause the output of comparator to activate, and in some other parts of the noise period it gets lower than the reference voltage and it turns the output off. This is why the relay turns on and off like crazy. But we can solve this problem by using only one resistor. Example number 11, Schmitt trigger resistor. In the ordinary comparator systems, there is one threshold voltage, like the reference voltage in the previous example. The sensor voltage is compared to the single reference voltage. But in Schmitt trigger comparators, we have two reference voltages.
This is an ordinary comparator using op-amp and a single reference voltage where the noise can find a way to the output. In this area the relay is off, in this area the relay is on, here the relay is off, but here is where the relay turns on and off like crazy, because in this area the sensor voltage can go higher and lower than the reference voltage periodically. But in a Schmitt trigger system, the output will be activated once the sensor voltage gets higher than the first threshold, and then the output will be turned off once the sensor voltage gets lower than the second threshold.
It seems very nice, but how can we make the system with two thresholds? This is the million-dollar question. The answer is very simple. Add an extra resistor. How do I do that? I'll explain.
By putting this Schmitt trigger resistor here, the output will be protected and the noise at the input will never find a way to output. By putting this resistor here, we will have actually two separate thresholds like this for turning on and off the output. You may ask how a single resistor can create two threshold voltages out of a single reference voltage. Let me explain. When the output is turned on, it means that the voltage at the output is close to VCC. So This resistor will pull this reference voltage up a little bit. And when the output is turned off, it means that the voltage at output is 0 volts. So this resistor will pull this reference voltage down a little bit. You may ask why I have used this specific value here, 28 kilo ohm resistor. Look, the answer is very simple. The value of this resistor has an inverted relationship with the distance between these two thresholds. The higher the resistance of this resistor, the closer the thresholds will be. Look, the relay turns on and off like crazy. Now I'm gonna use this resistor here. The problem is completely solved. Now the relay is turning on and off clearly.
Isn't it beautiful? Yes, it is. Anyway, there are endless examples of resistive sensors. Resistive humidity sensors are resistors that are sensitive to humidity. Carbon microphones, resistive touchscreens, load cells, and shunt resistors are some other resistors that are used as a sensor. Anyway, I've already mentioned that resistors are used to limit current and protect other components such as LEDs or transistors. Similarly, there are some other kinds of resistors to protect the entire circuit against high voltage. Example number 12, resistor as a high voltage protector. There is a special kind of resistor whose resistance depends on the voltage at its leads. They are used to protect the circuit from overvoltage.
This is a voltage-dependent resistor. It's also called a varistor. It has a nonlinear varying resistance dependent on the voltage applied. Each varistor has a nominal voltage rating that indicates the voltage threshold that makes this component to pass current by decreasing its resistance. For example, if the nominal voltage is 100 volts, it means that the varistor has a very high resistance when the voltage across its leads is lower than 100 volts. Look here, this area, and has a low resistance when the voltage across its leads is higher than 100 volts. Look, this area. Look, this is a 39 volt varistor, meaning that when a voltage higher than 39 volt is applied to its terminals, the resistance between its leads will decrease drastically and it will pass the current to protect the circuit by preventing high voltage from reaching the main circuit.
Usually a varistor is placed at the power input of the device and parallel with the power line to protect the entire device from overvoltage. Anyway, the next example I'd like to discuss involves the application of resistors when discharging a capacitor. It seems weird, right? Why should someone use a resistor to discharge a capacitor? I'll explain. Example number 13, using resistors to save lives.
This is a capacitive dropper circuit, also called a transformerless power supply. When the main power is applied to the input, this capacitor will pass the AC power to the output, and when the power is off, the capacitor is still charged to a high voltage. It's dangerous if somebody touched the capacitor by mistake. So, we have to put a resistor in parallel with the capacitor to discharge the capacitor gradually. This is another example. In the circuit, I have rectified the main power and used a capacitor for smoothing the output voltage. Also, this capacitor is charged to a high voltage, so I have to put a resistor in parallel with that to discharge the capacitor to prevent high voltage shocks.
It's so important. A resistor can save a life. Anyway, the next example I'd like to explore is the application of resistors in measuring time. Example number 14, resistors for making delays.
This is another example where a resistor is in parallel with a capacitor. Here the resistor is used to discharge the capacitor gradually to measure time or to make a delay. The higher the value of this resistor, the more delay it creates, and the lower the value of this resistor, the higher the speed of discharging this capacitor.
The next example I'd like to delve into is the role of resistors in adjusting an adjustable regulator. By referring to the datasheet of any adjustable regulator, we can find some resistors that are used to determine the output voltage. Example number 15, adjusting regulators.
To charge these batteries, we have to make a proper voltage, say 4.2 volts. Since this voltage is not a standard voltage, we need to regulate a higher voltage to 4.2 volts. There are numerous regulators to use. LM317 is one of them. Look here at the datasheet for LM317. This is the basic circuit of an adjustable voltage regulator using LM317 regulator. There are two resistors here to adjust the output voltage. R1 has to be 240 ohms, and by changing the value of R2, the voltage at the output will change. It's a good idea to replace the R2 with a variable resistor like this potentiometer, so you can adjust the voltage at the output by turning the potentiometer.
Sometimes we need to determine the voltage of a node in a circuit when it is not connected to anywhere. Example number 16, using resistors as pull-up or pull-down. One of the most frequent uses of resistors, especially in digital circuits, is to use them to pull up or pull down some signals.
When you are driving a MOSFET, it's recommended to use a pull-up or pull-down resistor to determine the gate voltage when there is no signal on the gate. Because if the gate pin voltage is not determined, it's likely that it gets noise and turn on and off unpredictably. The reset pin of microcontrollers is usually active low, meaning that by syncing them, the microcontroller will reset, and by sourcing them, the microcontroller will work normally. To ensure that the microcontroller will work normally, we need to add a pull-up resistor to the reset pin. Also, at any button input, we have to put a pull-up resistor. However, in some microcontrollers, this can be done by software. When the button is in its normal state, the voltage here at this point will be equal to VCC because this point is pulled up to VCC using this resistor, and when the button is pressed, the voltage here will be equal to 0 volts because this point will be connected to ground directly through the button. In some protocols, you have to use pull-up resistors. The I2C protocol is a good example where we need to pull up SDA and SCL lines. These pull-up resistors are essential. The protocol wouldn't work without them for some technical reasons.
The value of pull-up resistors depends on many parameters, mostly on circuit requirements and the transistor type used to build a microcontroller. But in most cases, a 10 kilo ohm resistor would be a good choice. Even though there are endless uses of resistors in electronic circuits, we have discussed a very tiny portion of them because of time restriction. Anyway, we have reached the final moments of this video. I hope you enjoyed watching this video and learned something new. Thanks for watching. If you enjoyed this video, don't forget to hit the like button and subscribe to my channel for more contents like this. See you in the next video.